In this lesson, we're going to talk about the chi-square statistic, and I'm going to use a very basic example to help you better understand what we use chi-square for. So let's think about a coin. And we know that if we take a coin and we flip it several times, that we would expect 50% of the time, approximately, we should get heads, and 50% of the time, we should get tails. So let's say that we flip a coin 60 times, and this is what we determine. We end up with 35 heads and 25 tails. Well, that was 60 flips. And so 50% of 60 we would expect to be 30 heads and 30 tails. So is 35 and 25 a good fit to what we're expecting, which is 30 of each? Now, some people might say, no, I think 35 and 25 is not a good fit to 30 heads and 30 tails. And some people, might think it is. So when we use that chi-square statistic, everyone is going to agree as to whether the observed numbers that we're getting are a good or a poor fit to what is being expected. Okay. So this chi-square formula is on the formula sheet. You can see it right here. We want to make sure that you understand what those symbols mean. And just so you know, some of them are summarized for you on that formula sheet. The O that we see here is our observed numbers. So let's indicate the O means observed. The E means what we're expecting, so the expected. This symbol right here just simply means chi-square, so that X means chi. And then this symbol that looks like an E here means sums. We're going to add some numbers up. So again, that chi-square value is to help us determine if the numbers that we observe, the observed data, a good fit to the numbers that we're expecting or the expected data. All right, I'll talk more about this null hypothesis, but I think it's going to be easiest if we start with setting up a table. So when I tell students to do a chi-square, remember all you have available to you is on the formula sheet, you have the formula, and I tell students to set it up in a table. So they're not going to provide a table. You need to remember to make the table. So what we're going to do is in the first column, we're going to put our categories. So basically we have heads and we have tails. Now, according to our formula, we need we need observed numbers. We need expected numbers. So we're going to do a column for each. And then according to our formula, again, up here, it says that we need to subtract the two. So we're going to write O minus E. And then it says we need to square that value. So let's write O minus E squared. And then again, according to the formula, we're going to do that value that we just got, which is O minus E squared. And we're going to divide it by the expected number. Now, when I do a chi-square problem, you're going to see that in my expected column right here, I am always going to write a percent in the corner, my expected percents for each of these categories. We're expecting that 50% of the time we should get heads. So I'm going to write 50% in the corner, and we're expecting 50% to be tails. Now, it's not always going to be 50% when we do a chi-square problem. It could be 25 each time, or maybe we're expecting 25, then 50 and 25 of three different categories. Okay, so it's not always 50%. But I'd like to write that percent in the corner. So sometimes whenever you're trying to do a chi-square in the future and you forget how to figure out the numbers for the expected column, if you remember to write a percent in the corner, that's going to kind of trigger you to help you remember how to solve the chi-square. Okay, so to move this up, now, when we flipped this coin, we ended up flipping it 60 times. So I'm going to put the total number of coin flips that we have here. Now, to figure out the numbers in the expected column, so we can then calculate O minus E, is we're going to take 50%, or you can type in 0.50. That means the same thing on your calculator. Multiply it by this bottom total number, and then that will give you what we're expecting. Now, this one's easy to do in our head, but not all of them are going to be easy to do in your head. We should expect 30 of the 60 to end up being heads. And again, I'm going to take 50%, or whatever percent is in the corner here, multiply it by the total, and write in that value here, which is 30. Now, once you have numbers in the expected column, there is a way to check to see if you've gotten the numbers correct. Lots of times when we do a chi-square, this is the column. These numbers are what you're going to mess up, and then you're not going to be able to get to the correct answer. So pause and see if you add up your two columns, if these two numbers match. So we add up 30 plus 30, that gives us 60. If these match, or if these are the same, then go ahead and proceed doing your calculation. If those two numbers, when you add up those two columns, don't match, then you need to figure out what you did wrong. Now I'm going to clear this because I'm going to show you what a lot of people do wrong. So we end up with having that percent in the corner, 50% and 50%. And so people will take this 50% and they times it by this, and they'll put a number in here. But that's not what we're going to do. Remember, we have a total here. We had 60 coin flips. So we have to figure out, if we're expecting 50% of those 60 to be heads, that is a total of 30. And then again, 50% times that 60 would give us 30. So again, when you add up those columns, these should end up being the same. And now we need to do simple math. So O minus E. We have 35 minus 30, so that's going to give us 5. And 25 minus 30 is going to be a negative 5. Now you can put the negative in here, but we are about ready to square that value, and our negative is going to disappear. So if you don't put the negative there, then you're not going to be counted off. So 5 squared, 5 times 5, is going to give us 25. Same here, negative 5 squared is 25. Now for this last column, we have this O minus E squared value. That's this top number. So we're going to do 25 and then come over here, and it looks like we're expecting 30. So 25 divided by 30. And the same for the next row. Our O minus E value is 25. And our expected in this case also is 30. And we're going to divide. 25 divided by 30 is 0.8. And we also get that right here. Okay, now remember, when we take a look at our formula, we had this E, and that meant sum. So those two values we're going to add. I like to put an addition sign and an equal sign, and that just helps you remember every time, my last step here. So my chi-square value that we're getting is 1.6. Now, before we talk about what you're going to do with that value, let's talk about the null hypothesis. Many times you will be given an experiment and they're going to ask you to write the null hypothesis. Now, let me give you a reminder of what the word null means. The word null means no or none. So for example, let's say that we had a signed contract between the two of us and we decided to no longer, have that contract. It's now void. We can say that contract is null and void. That means that there's no contract anymore between us. So when you see the word null, you need to think the word no. So if I ask you to write the null hypothesis, then you're going to state that there is no difference in the number that we are observing. So in this case, we're observing 35 heads and 35 tails, and what is expected. And I encourage students to list what's being expected, and that's just to make sure that you don't make a very common mistake on a test whenever you're doing a chi-square. So for my null hypothesis, I already have part of it typed out for you. There is no significant difference in the number of heads and tails observed. Again, that's 35 heads and 25 tails, and what is expected. And we can say, and what is expected, which is 50% of each. Or you could say, what is expected, which is 30 heads and 30 tails. Okay. So any variation, so 35 and 25 compared to 30 and 30, any variation between those two sets of numbers is just due to chance. I promise we'll practice some more null hypothesis. All right, now that we have our chi-square value, let's talk about what we're going to do with that. So we can make the decision whether 35 and 25 are a close fit to 30 and 30. Before we can do that, we're going to have to figure out how to use this chi-square table that you see right there. And it is also on the formula sheet. So right here underneath, you're going to see that chi-square table. Now, you need to understand what these numbers mean and what we call each of these different sets of numbers in the table. So the first thing you have to figure out is what's called the degrees of freedom. And to figure out the degrees of freedom, it is going to be n minus 1. And n means the number of groups that you have listed in your table. We have two groups. We have heads and we have tails. So n equals 2. So to figure out our degrees of freedom, we would do 2 minus 1 for this problem. So our degree of freedom is going to be 1. In our chart, these numbers that you see here, like 1, 2, 3, those are the different degrees of freedom. So if I ask you to indicate the degree of freedom, you're going to say 1, 2, 3, 4, 5. You're not going to say like 3.84 or 5.99. Those are not degrees of freedom. The second thing you're going to have to remember is which p-value we're going to use. Now, in science, we are always going to use a p-value of 0.05. You are never going to use the numbers that are off of this bottom line. And what it means when we use a p-value of 0.05 is that when we are about ready to make a decision, again, whether 35 and 25 is a good fit to 30 and 30, or if those numbers are too far off, that whatever we decide, we're going to be 95% confident in our decision. That is the level of confidence that's acceptable in science. To kind of give you a perspective, imagine if you go to a doctor and the doctor says, I am 95% confident that this is going to be a successful procedure for you. I imagine you feel, pretty good about that confidence level. Well, then imagine if your doctor says, well, I'm 67% confident that I'll be able to perform this operation. Well, that's not good enough, right? So in science, we have a confidence level that is acceptable, and that is 95%. We have to be 95% about the decisions and the conclusions that we make about our data. So that is why we're always going to use a p-value of 0.05 because we need to be 95% confident in this decision we're going to make. All right, so now that we have two values, so we figured out p equals 1. I'm sorry, let me say that again. My degree of freedom is 1, and we're going to use this p-value of 0.05. Then we see this intersection here with this number 3.84. These numbers, like 3.84, 5.99, 7.82, these numbers are called the critical values. Critical values. So if I ask you to determine the critical value, you're going to say for this experiment, it's 3.84. If you do a different experiment where you had 3 categories listed here, you're going to find your critical value is 5.99, etc. Okay. So here we finally have this critical value, and then I have my chi-square value, 1.6. So now that I have those two numbers, this is what you need to remember to do. We're going to compare them. So we have to compare our critical value and our chi-square value. If your chi-square value, so 1.6, if it is lower than your critical value, then what that means is you're going to accept our null hypothesis. Remember, our null hypothesis up here said these two numbers, 35 and 25, are a good fit to 30 and 30. There's no significant difference between them. Okay? So that's what we would be when we accept our null hypothesis. We're saying 35 and 25 is a good fit to 30 and 30. And that's the conclusion that we're going to make because our chi-square value is below the critical value, which is 3.84. Any variation, the fact that it's off 5, is just simply due to chance. If you flip a coin, 60 times, there is just a good chance that you're going to end up with 35 and 25 and not be exactly at 30 and 30. So since this is the conclusion that we draw, I'm going to go ahead and just kind of put a check mark. This is what we determined or concluded for this problem. But let's assume that our chi-square value was much bigger than that 3.84. If that's the case, I have summarized here what we would do. We would reject the null hypothesis. And what that would mean is, remember, our null hypothesis says 35 and 25 are a good fit. There's no difference between those numbers in 30 and 30. If we reject that, then what that means is 35 and 25 are too far off from 30 and 30. Now, since we didn't determine that, let me clear this. Then let's go ahead and put an X through this because this isn't what we decided for this problem, okay? We accepted, we didn't reject the null hypothesis. If we did reject it though, then what that means is, in relation to an experiment, is that you need to try to find some kind of explanation as to why you're not getting 50 heads and 50 tails. Maybe the person isn't flipping it right. Maybe it's a trick coin. So again, when we reject our null hypothesis, that leads to, further, questioning and experimenting, trying to figure out what is causing the difference between what we are getting and what we are expecting. Okay, so sometimes in an APSA question, you're going to see a question and they're going to ask you to accept or reject the null hypothesis and then justify your explanation. Now, when you write your answer to this question, it's pretty easy to do the first part. So you're going to say, I accept the null hypothesis. Now, when they say to justify, this decision, then there's quite a few things that you have to remember to answer or indicate. So you have to prove to your grader that you basically knew what you were doing, that you knew how to figure out the critical value is 3.84, and that you knew to accept the null because your chi-square value was below the critical value. Okay, so when you go to justify why you accept or reject your hypothesis, okay, you need to, one, indicate how you figured out that critical value. So you need to mention that you used n-1 to determine 1 degree freedom. You need to indicate that you knew to use that p-value of 0.05, and that is what helped you determine that critical value of 3.84. So what I did here is I wrote a model answer so you can see how you would need to justify your decision on whether you would accept or reject our hypothesis. So you accept the null hypothesis because that chi-square value of 1.6 was lower or less than the critical value of 3.84. And then you got to explain where that number came from, that you know how to use the chart. And that 3.84 was determined by using n-1 to determine there was 1 degree of freedom, and then using that p-value of 0.05. Now, I want to show you what a real example related to chi-square is going to look like on their test. You're not going to have any questions about coin flips because this is biology and we are studying living things. So you're going to be given experiments about living things. So for example, here we have fireflies in this example. And to summarize, they want to see if we put fireflies in different temperatures, if it's going to affect the amount of light that they emit. Now, I feel like this is a pretty easy example because obviously the IV is the temperature, and then the DV is the amount of light that the fireflies emit. Now, if I ask you to write a null hypothesis, remember, null means no or none. Well, to help you maybe better understand this null hypothesis, let's just review how you would write a typical hypothesis that you've written in the past. So some of you might say, well, as temperature increases, the amount of light emitted by the fireflies will increase, or you might say decrease. Okay. So you're predicting about which temperature is going to have the greatest amount of light emitted or maybe the least. Remember, the null hypothesis is you're basically going to say, no, there's no effect on temperature on the amount of light or temperature will not affect the amount of light that a firefly emits. Okay. So we need that word null or no. There's going to be no effect or no difference in the amount of light emitted from fireflies if there is a change in temperature. Okay. So a good example, or a couple good examples that you can write for the null hypothesis is here. Temperature will have no effect on the amount of light emitted by fireflies. Any variation is due to chance. Or you can say there will be no significant difference between the amount of light emitted by bees in different temperatures. Again, any variation is due to chance. So here's another example. And what they're doing is they're taking plant cells and they're exposing them to different amounts of CO2. And they want to see if it affects the number of mitochondria that will develop in the cells. So I want you to take a second to see if you can write the null hypothesis for this experiment in this box. I've written in a good null hypothesis for this experiment, so hopefully it matches something to what you wrote here. So again, null means no. So we're going to say that CO2 concentration has no effect on the number of mitochondria in cells. Any variation is due to chance. You could also say there's going to be no difference in the number of mitochondria in cells that have been exposed to different amounts of CO2. So either of those is a perfectly acceptable null hypothesis. Now, next I wanted to show you another experiment that uses chi-square, again, about living things. So here we have an example where they want to see if bees are attracted to caffeine that can be produced and found in the nectar of flowers. So they've set up a situation where we have fake flowers and we've added nectar to them with different amounts of caffeine. Since we just got done talking about the null hypothesis, let's review again what a good null hypothesis would be to this experiment. Remember, null means no. There's going to be no effect. Okay, so you can say there's going to be no difference in the number of visits by the bees to flowers that contain different amounts of nectar. So again, their IV is changing caffeine concentration, and our DV is going to be the number of visits by bees to that flower. Or you could say caffeine is going to have no effect on the number of bee visits to each flower. Any variation is due to chance. Now, if you take a look at the data that we see here in our table, if I asked you to draw a conclusion, I would say that most people are going to say that as caffeine is increased, then the number of visits by bees to that flower is going to increase. And so they might conclude that caffeine is having an effect on the number of bees that are visiting a flower. Well, some people are going to say, no, I actually think it's pretty even. Just that variation that we see there between the flower is just due to chance. So again, that's why we're going to use a chi-square so that we make the same decision just based on this statistic. Let's see if you guys remember that formula and how to use it to figure out the column headings in a table. So again, we're going to draw a table. They're not going to provide the table for us. And we need to indicate what was the observed, the expected. The formula says subtract those two. So write O minus E. O minus E squared is the next part. And then it says to do that value, O minus E squared, and divided by the expected. Let me move this down a little bit here so that we can see our numbers here so we know what to fill in our chi-square table. So let's indicate our variables that we're testing. So we're doing 0 micromoles is what that means of caffeine in nectar, 0.1, 0.2, and 0.3. And it's indicating that we observed 38 visits, 41, 43, and 46. This is the data that we collected. Now, if we're hypothesizing there's going to be no difference in the number of visits per flower, and we've got 4 flowers, does it make sense that if the bees don't have a preference, then 25% of the time we should see, or 25% of the visits should happen to this first flower, and 25% of the visits will happen to the second flower. And so this is indicating that the bees don't have a preference. They're going to each flower basically equally, even though the flower contains different amounts of caffeine. Now, once we have those percents up in the corner, we got to remember what to do to figure out our numbers that we're supposed to put here in our expected column. This is where students commonly mess up. Let's see if I can move this up a little bit. What often happens is students forget to add and figure out what this total number of visits was. So in this case, it was 168. Oh, hi, Butters. Say hi to my students. It's my cat. So we got to take this percent and we have to multiply it by that total, and that's going to give me that number that we're expecting. So 25% of 168 is 42. So if we have 168 visits to those flowers and the bees have no preference and they're just evenly going to each flower, then we would see that we'd get 42 visits at each of those flowers. And again, how I'm figuring that out is I'm just taking that percent, so 0.25, multiply it by the bottom number, and then it tells you what to go or what to put in that box each time. Okay? Just do it over and over again. Again, this column is what students commonly mess up. So this is how you can figure out if you're on the right track. You need to add up both of those columns. So here my total, when I add them up, is 168. So that checks. If these numbers, these totals are the same, then keep going with your calculations. Otherwise, you need to go back, and I guarantee you what you've messed up is you've messed up the numbers that you put in that expected column. Now that those columns match, we can do our math. So O minus E. So again, when we do 38 minus 42, we're going to get a negative number. So we don't have to put -4 here, but you can. But again, we're about ready to square that value, so that negative is going to disappear. The difference between 41 and 42 is -1. So 43 minus 42 is 1. And then we have 46 is what that was. Minus 42 is 4. All right, so now we're going to square each of those. So this is going to be 16, 1, 1, and 16. So in this last column, it says take that value. That's that top number now. So I like to write 16, and I need to go over to my expected, and it looks like I'm expecting 42. And again, this isn't always going to be the same number. I'm going to give you an example where that's not the case when we do a chi-square problem. So I need to make sure that I just don't write this for 1 and then write it all the way down that column. So in this case, my top number is 1 and my expected is 42. So I'm going to do 1 divided by 42. And then again, this one's 1 divided by 42. And then I have a 16. So that's 16 divided by that expected is 42. Now let's solve, because when I get those numbers, remember that E on our formula sheet that we see right here means we're going to have to add those up. So solving those, this is 0.38, 0.024, 0.024, and 0.38. Okay, again, just to help me remember what I'm supposed to do here, if I have one of these problems on the test, I like to put my addition sign there and my equal sign. When I add those up, this symbol means chi-square. My chi-square value that I get is 808. Now we have to remember what we're supposed to do with that statistic. All right, so let's move this up. I need to look at some of those values here. So now we need to remember to get our degrees of freedom because we've got to figure out and use this chart. Remember, to figure out our degrees of freedom, it is n minus 1. And so in this case, we've got 1, 2, 3, 4. So n equals 4. So 4 minus 1, we're going to get 3 degrees of freedom for this experiment. The p-value that we always use is 0.05. And so where this degree of freedom of 3 and that p-value of 0.05 intersect is 7.82. So that is called our critical value. So 7.82 is the critical value. Again, 0.05 is called the p-value. And then this 3 is what we call the degrees of freedom. You need to know the names of these numbers. And my chi-square value was here, right? 0.808. All right, now we have to remember what we're going to do with those two values. So we have 7.82 and then we have 0.808. We have to compare them. And in this case, just like with the first one, we can see that our chi-square value is much smaller than our critical value. And we have to remember that if that's the case, then that means that we're going to accept our null hypothesis. So what that means is these numbers that we got here are actually a really good fit to no preference numbers, as 42 visiting each of those flowers. This means caffeine is not affecting whether the bees are visiting the flowers or not. They're just randomly going to each flower, which when we started this experiment, when you looked at these numbers, I indicated that a lot of people would say, yeah, it definitely looks like the bees are going to flowers that have more nectar. But when we accept our null that says these numbers are a good fit to this, that the caffeine level is not affecting the number of visits. When we accept that, that just means that caffeine is not affecting the movement of those bees. Okay, so now this says justify our decision. So justify whether we accepted or rejected the null hypothesis. I want to go back and kind of refer to everything that you have to mention when you go to justify or explain why you accept or reject your null hypothesis. So you need to indicate that you found this critical value, what it was, how you figured out the degrees of freedom, and that you knew to use that p-value of 0.05. And that gave you this critical value. And if that chi-square value was greater or less than the critical value, then that told you that you needed to accept or reject the null hypothesis. To save time, I went ahead and wrote kind of this model justification. This is what I would expect you, to write if you have to justify that decision. So again, you can see that I mentioned that my chi-square value was lower than the critical value. And then I talked about how I figured out that from this table here. So I knew to do n minus 1 to determine there was 3 degrees of freedom. And then I knew to use that p-value of 0.05. So we're going to be 95% confident that we should accept the null hypothesis. Caffeine is not affecting the movement or the number of visits a bee makes to each flower. All right, so just one more example, and most of it's written out. I just want to kind of talk through it and have you pay attention and not be so concerned with writing down a bunch of notes on this page. The question is, or the experiment is about snails. And when we release snails into the water, do they prefer to move upstream or will they start to move downstream after they're released? And so here is our observed number. So we've done this experiment. So again, O means observed. So I'm going to put these observed numbers in this observed column. But I want to show you something So you note that sometimes they'll list data in a way that's a bit tricky. And so if you're rushing through this problem, you might have written down upstream is 26 and downstream is 39. But that's not what it's saying. It's saying 26 out of the 39 snails that were released were recovered upstream. So let me move this up a little bit here. And so that is why I don't have 26 and 39 written here. I have 26 and then 13 would have gone downstairs, or sorry, downstream. All right, let's take a look at what this essay question is asking you to do. Remember, they're going to use letters to indicate the different parts of an essay question. So there's 3 parts to this. And then following that essay question, you're going to get a bunch of blank lines, and they're not going to provide a table or anything. If they ask you to solve solve a chi-square problem, then you would actually just make this table here amongst the lines where you can write your answer. When we write or answer a section of our test, we want to make sure that we're using the same letters so the grader knows what part of the question you're trying to answer. So it says, write the null hypothesis for the experiment. Remember, null means no. So we could say there's going to be no difference in the number of snails that move upstream and downstream. Okay, so, or you can say the snails do not have a preference. There's no preference in movement once they're released into the stream. Any variation between what we are observing and what we're expecting is due to chance. Now, we would go and we'd set up our chi-square table that we see here. We got to remember, again, how to use the formula to figure out the column headings. And I just want to note that in this case, if we're assuming they don't have a preference, then when we release them, 50% should have gone upstream and 50% should have gone downstream. My total number of snails was 39. Now, I did this problem and I use these numbers because I want to show you that sometimes in expected, you're going to get a decimal. And, this is a pretty significant value if you're only dealing with 19. So don't just get rid of that decimal because that's going to make your chi-square be greatly different if you are rounding too much. So we're going to use that decimal in here. So I'm going to take 0.50 times 39, and that should give me 19.5. 0.50 times, again, that total gets me 19.5 again. And I need to add those up to make sure that those values of those 2 columns are the same. So that would give me 39. I check these values are the same or they're very, very close, so I can go on with these calculations. So when I do my math here, I end up with that chi-square value of 4.32. And then we got to remember, because we wrote the null, we calculated the chi-square value, but now we have to determine whether we support or accept the null hypothesis or we reject it. We had 2 categories here. Okay, so to figure out my degrees of freedom, it was n minus 1. So that means we have 1 degree of freedom. Okay, so I'm going to use that column. I always use that p-value of 0.05. My critical value is 3.84. So now that I know that's my critical value, if you look here, now we have to compare these. And it looks like my chi-square value is greater now for the first time in these examples. It's greater than that critical value of 3.84. So if that's the case, we're going to say the null hypothesis was not supported. We reject the null. The null says that they don't have a preference, that they would evenly go upstream and downstream, but we're rejecting that. So the snails do have a preference. They significantly more often swim upstream than they do downstream. Okay. So when we go to justify this decision, then we'd say that because our chi-square value was greater than that critical value, and we determine that again from using n minus 1 to determine 1 degree of freedom, and then we use that p-value of 0.05, that's why we knew to reject the null hypothesis. Now, when we reject a null hypothesis, that is what leads to more questioning from the researchers. So why? Why are they significantly swimming upstream more than downstream? So we can then design further experiments to see if we can figure out what is the stimulus or the reason or the benefit for them to swim upstream versus downstream.